Welcome to this afternoon session. And we are honored to welcome Professor Chi-Wang Shu, Theodore Stowell University Professor of Applied Math at Brown University. As a pioneer in computational PDEs, he co-developed the foundational Wino schemes. His distinctions include the Siam John von Neumann Prize, fellowships in Siam, AMS. He was an invited speaker at the 2014 ICM. His paper, essentially non-oscillatory and weighted essentially non-oscillatory schemes, was awarded Frontiers of Science Award this year. And so please join me in welcoming Professor Shu.
Thank you very much, and it's a pleasure to give this talk. So I will give a survey and talk about the recent developments of Wino schemes. This doesn't work. Anyway, this. Okay, so here is an outline. So I will give an introduction and now it works. Okay. Give an introduction, then I will talk about the Wino approximations and then the scheme. So Wino is actually itself is not really a scheme for solving PDE. It's an approximation process, but it is used to form an algorithm to solve PDEs. So here's an introduction. As I said, Wino procedure, weighted essentially non-oscillatory procedure, is an approximation technique. It's mainly used to solve hyperbolic and other convection-dominated PDEs. For example, this convection equation, hyperbolic conservation law, for which U is could be a vector or scalar. If it is a vector, then f prime of U would be the Jacobian, would be a matrix. So you would assume that this linear combination of the three Jacobian matrices with any real coefficients would be diagonalizable with real eigenvalues and a complete set of eigenvectors. So this is an assumption. Fortunately, many physical systems would belong to this class. So there's a wide applications in computational fluid dynamics and many other areas. The main difficulty of solving this PDE is that the solution may have discontinuities. So discontinuous solutions would arise. So this is regardless of how you prepare the initial and boundary conditions. So generically, if you give an initial condition, arbitrary initial condition chances, so it's almost surely you will just get a discontinuous solution. If you want a globally smooth solution, you really need to prepare your initial condition. So this is the main difficulty. Like I will explain later. So actually you would want to get an algorithm for solving hyperbolic equations, hyperbolic conservation laws in finite difference or finite volume or discontinuous Gaultian finite element methods. Looks like a complicated job, but the starting point, the building block is actually an approximation problem. I will try to explain how it can be decomposed into simple building pieces. So this would be just a building piece. This Wino technique is a building piece. This actually in 1D interpolation can be explained in a very elementary fashion, which you teach in college in microanalysis courses. Just the interpolation. So if you are given point values of a function at the grid points x equals to xj, which may or may not be uniformly distributed, these grid points, you only know the value of the function at those nodes, nothing else. And the idea is that you want to build a piecewise polynomial, pj, which belongs to this interval xj minus half, xj plus half, which xj minus half is halfway between xj minus 1 and xj. So in this interval centered with xj, you would want to find a polynomial pj of x, which suitably approximates ux in this cell. Remember, you only know the point values of the function, nothing else. You want to build piecewise polynomials, which can do the job. It's of course very elementary, right? So interpolation. There is an associated problem, slightly more complicated, but not much. So it is called reconstruction. So this time, you're not given the point values of the function, you are given the cell averages of the function. So integration of the function over a cell divided by the cell length. So you don't know the function itself, you are given numbers which corresponds to the cell averages of the function in different cells. So again, the problem is the same. You would want to find a polynomial Pj of x defined on this cell ij such that it approximates the original function ux suitably over this interval. So I have posed the two approximation problems. One is the very well-known interpolation problem. The other is a little bit less well-known reconstruction problem. So I posted, of course, in 1D, but you can imagine that same problem would exist in multi-dimensions and in over-structured or unstructured meshes. So let me put a wish list, right? So you are saying, okay, I want such an approximation, Pj of x. What do I want this Pj? What properties do I desire that this Pjx would hold, right? So this is the two pieces of wish list. The first wish list is that I want it to be high order if ij, this cell, happens, the u of x, the original function u of x happens to be smooth in the cell ij. So if it is smooth completely in cell ij, I would want the Pj of x to be high order accurate. But I also want another thing. Remember, my function is not really everywhere smooth. It has some discontinuities. So the generic situation is that it has a couple of discontinuities, several isolated, but between them, the function is very, very nice. So it's really, you can have plenty derivatives, in between. However, if I perform the interpolation or reconstruction just in the naive way, I find out that I'm okay in smooth regions a little bit away from the discontinuity, but near the discontinuity, I will see these oscillations. So if I have this function, I know these values. Let's say interpolation. And then let's say I used this 1, 2, 3, 4 to build a polynomial of degree whatever. Should be this way. Interpolating these 4 points. I find out that I'm okay right here and here, but if I concentrate on this interval from here to here, my approximation is overshot. Did I get it right? Yeah, something like that. Overshooting, right? So this is called Gibbs phenomenon. Actually, it's a very famous thing in spectral methods. But it also happens if you do interpolation with just finite order of accuracy. This Gibbs phenomenon is, there are some properties of this Gibbs phenomenon. First of all, this overshoot, if you refine the mesh, you put these circles closer to the discontinuity, the height of this overshoot does not change. It is always a fixed percentage of this height, whatever percent, 13, 7%, whatever percentage, this you can prove. So if you push the points towards this is a great refinement, right, towards the discontinuity, you still see the same overshoot, but it's closer to the discontinuity. The height doesn't change. So this is why it's called Gibbs phenomenon. You see, if it's a fixed height of overshoot, it's a real overshoot, right? It seems that you cannot overcome this overshooting with great refinements. So that's something which you really don't want. So this second wish list, saying essentially non-oscillatory near discontinuities, is that I don't want to see this fixed. So either you have some overshoot which will decrease when you do great refinements, or you don't have overshoot at all. If you don't have overshoot at all, it will be called non-oscillatory. If you have a little bit overshoot, but this height decreases when you refine the mesh. If this height is no longer, let's say, 10% of this total height, which this height never changes, so the 10% never changes, that's not good. If this height is delta x to the high power, k being the order of the scheme, then that's fine, right? Because you are making this kind of errors also in smooth regions. So if you have this kind of overshoot, that's tolerable. So if that is the case, the scheme is called essentially non-oscillatory. So roughly speaking, essentially non-oscillatory means that you cannot see the oscillations with not a magnifying glass. So if you draw the picture, you don't see any oscillations, but if you zoom in, you see, okay, it's not really non-oscillatory. There are some wiggles, but the wiggles are very small. So that would be fine. So this is my wish list, just two properties. Seems to be simple enough, right? And yeah, so we know it's a procedure that explain what it does, but it's a procedure to obtain such approximations. The very first paper on Wayno schemes is this paper by Xudong Liu, Stanley Ocean, and Tony Chen in 1994. So which designed the third order Wayno reconstruction. Then this following paper by Guangshan Jiang and myself in 1996 systematically designed arbitrary order. Well, arbitrary order, however, the fifth order is built in this paper as default to build Wayno schemes. Which is probably, so then the Wayno scheme got picked up. There are many later developments and applications, but mainly the backbone is the scheme in this paper. I wrote this, so this paper on survey, basically on acta numerica with some new developments. That's the paper being awarded the prize. But it's I would say the work is over many years to develop this sequence of methods. Let me explain what this Wayno approximation. You see these two targets, right? Two set of goals. So how do you achieve that? Let's come back to this interpolation problem, which we call problem one. So remember, it is called that you have the point values, the circles of the function, and then you want to find a polynomial to approximate either ux or its derivative or its integral. So through a polynomial. Interpolation, so usually the usual literature on hyperbolic equations, they don't start with interpolation, they start with reconstruction. Later I will explain why it starts from reconstruction, because the very well-known scheme of finite volume actually does not use interpolation, it uses reconstruction. However, interpolation itself is not useless. It's, well, for one thing, it's easier to explain. For another thing, it is actually used in one type of finite difference Wayno scheme, the so-called A-Wayno, alternative Wayno scheme, which has been picking up attention over the past 10 years, that it has certain advantages in solving a certain class of problems, including non-conservative hyperbolic equations, and also for Hamilton-Jacobi equations. Jacobi equations, basically you use interpolation, you don't use reconstruction. Okay, problem two is, like I explained, is the reconstruction. You are given cell averages, and then you are going approximations. Let's say you want the approximation polynomial evaluated at the cell boundary, so, or the integral of the of the polynomial over, let's say, half of the cell, or whatever quantity that you would need in your scheme. If you have a polynomial, you can do many things, right? If you have a polynomial, you can find its derivative, you can find its integral, you can find many values of the polynomial at any given point, so on. Okay, so let's start with the description of problem 2, because it's used a little bit more in solving hyperbolic conservation laws. But the procedure is almost identical. So if you explain one, you basically get the same algorithm, very similar algorithm for the other. So the reconstruction turns out to be quite simple. So what you do is that you first say, what is the procedure that I will do to do the usual interpolation or reconstruction? The usual interpolation or reconstruction that you learn from elementary numerical analysis is that you first have a stencil. Let's say here, I will say the stencil has 3 cells, I minus 1, I, and I plus 1. Or if it is interpolation, I have 3 points, 1, 2, 3. So it's I minus 1, I, and I plus 1. Then I would say I want to find a unique polynomial. If it is interpolation, then it will be the polynomial which will go through this 1, 2, 3 points. So maybe it's this one. this polynomial. No, it won't be, because if it's 3 points, it has to be a polynomial which is quadratic. So the quadratic polynomial won't look this way. It will only have one extreme. But you can imagine that there is one and only one quadratic polynomial which will agree with values at these 3 points, right? That's only one. Maybe it looks like this. So that's interpolation. Now, reconstruction, very similar. So you will say you want to find a polynomial P whose cell average over this cell will equal to U bar I minus 1, whose cell average over the middle cell would equal to U bar I, and whose cell average over the right cell is equal to U bar I plus 1. So 3 conditions. If you write Px as A plus Bx plus Cx squared, so 3 coefficients to determine ABC, certainly you solve a linear system, you will get this polynomial Px uniquely, right? You can even do smarter things to write down this polynomial straightforwardly in Lagrangian form, Newton form, and so on. So they can do that. So there's no ambiguity here. Px can be constructed. So this is in 1D. In multi-D, there are also ways to construct this Px. If you are given a stencil, you can construct the Px having the property that you want, approximation property that you want. Now, then once you have the polynomial, you can do anything. So if your target is to find the value at I plus half, then just read the polynomial at I plus half. If you want to find it at I plus 1 over 4, just read the value at x at I plus 1 over 4, right? So you can do anything. You can do integration, you can do differentiation, you can do anything that will be needed by your algorithm. You might say, oh, this might be a little bit complicated. I need to solve a linear system of these 3 unknowns, 3 equations to find the polynomial P. I need to evaluate the polynomial P to get the value. It could be costly. But if you think about it, this is a linear procedure. The procedure to map the 3 cell averages, these 3 numbers, to this value, ui plus half, is linear. If it is linear, there must be 3 coefficients independent of your data that would make this work, right? Has to be linear. So you just have to find these 3 numbers, and then you find out these 3 numbers through whatever way, Lagrangian polynomial, Newton polynomial. Find out that for uniform match, it's actually minus 1 over 6, 5 over 6, 1 over 3. So at the end of the day, when you do coding, so he was talking about using AI to do coding. I guess you just tell AI, this is the formula. Then writes the coding for you. If you say interpolate, and then I don't know if it will do that. Maybe it will also do that. Anyway, but so this is, end of the day, this is so simple, right? So you get this thing. Now, it's not symmetric because it's I plus half is not symmetric in the stencil. Yeah, so it has one cell to the left and only 2 cells to the left, only 1 to the right. Okay, so then, yes, if you do it straightforwardly, it would build a matrix and solve that matrix. But there are better ways. Yeah, using Lagrangian, you can write down the coefficients directly, actually. Yeah. Okay. Now, what would be the problem of this procedure? You can say, okay, then I solved all the problems, right? So if I want a higher order, I just pick more points or more cells in the stencil. So let's say if I need the 5th order, I just pick 1, 2, 3, 4, 5, and build a polynomial of degree 4 using that procedure, and I'm done, right? You are done, except that if your stencil crosses this discontinuity, you will see this Gibbs phenomenon. So that is the drawback, right? Otherwise, yes, you are done. If your problem is smooth, you are done. Now, if your problem is not smooth, then what is this Wayno procedure? Well, the Wayno is doing the following thing. It says that, okay, I compute not just one approximation, but several. I compute an approximation using j minus 2, j minus 1, and j in this stencil S0. And I do build another approximation through the stencil j minus 1, j, and j plus 1, which stencil is called S1, and also stencil S2 of these 3 points. So I build 3 polynomials based on 3 different stencils. Build 3 polynomials rather than 1. Each of them would be a 3rd order approximation if the function is smooth in their, let's say if the function is smooth in this stencil, then it will be order 3 approximation. Okay. So then I write down these 3 approximations, right? I mean, you figure out those coefficients in the way that I described before. So you write down all these 3 approximations. You can use either one of them. It will be a 3rd order approximation if the function is smooth in that corresponding stencil. But I don't want to use any of them, at least if straightforwardly, because I don't know, right? I don't know about the smoothness of the function. Okay, I would also want to build another approximation, which is, let's say I already built 3, right? One is of this stencil, the other is this stencil, the 3rd one is this stencil. So 3 stencils, I build 3 polynomials, but if I combine all the 3 stencils, they have overlaps. So if I combine all the stencils, there are 5 points or 5 subcells, I can build a polynomial of degree 4 in the same way, right? So then I would get an approximation at I plus half, which is degree 4. Now, I have to do a lot of redundant work. I have 3 small approximations and 1 big one. They are related. So you figure out that they are so-called linear weights, gamma 0, gamma 1, and gamma 2, such that if I linearly combine the 3 small approximations, I will get the bigger interpolation result. So it's not surprising. If I have 3 3rd order approximations, if I pick suitable coefficients to sum them up, I actually get a 5th order approximation. You can work out the details. It's the coefficients, you can work them out. For uniform mesh, these are actually the coefficients, so you just get this. So far, I didn't do anything, because if I really want to use this UI plus half, I don't have to go through this middle step of building 3 small ones and linearly combining them. I just use the procedure directly on the 5 points. I will get the same approximation. So you are not gaining anything by writing the 5th order approximation as the linear combination of 3 3rd order approximations. You gained nothing so far. However, this procedure tells you that you can do something a little bit smarter. So you change this gamma 0, gamma 1, and gamma 2 into W0, W1, and W2. Just change the letter. But change the letter meaning change the meaning. So you basically say, I want this property, 1 and 2. The first is that if your function ux is smooth over all 3 stencils, in other words, it's smooth over the wider, larger stencil, then I really hope this wk is gamma k, because then I would get 5th order accuracy. So you would want it to be close to gamma k, not exactly the same, but this is close. You want it to be this close, which will guarantee 5th order accuracy. So this is desired list number 1. The other desired list is number 2, is that if there is a discontinuity here, so it will be the discontinuity is in the 3rd stencil, but not in the 1st stencil, not in the 2nd stencil. Then I hope this W3 is essentially 0. I don't want this guy, because this substencil contains a discontinuity. I don't want its contribution at all. So I want W3 in this case to be 0, well, not exactly 0, but it has to be small. In particular, it turns out to be this small. So if the discontinuity is here, let's see where, yeah, I think here maybe, then it is in the 1st stencil and also in the 2nd stencil, substencil. Then I want W1 and W2 both to be this small. So only W3 is big. You might say, what happens if the discontinuity is in the middle? In that middle cell, common to all 3 substencils. Then what? Then no matter how I choose W, it will contain discontinuity, right? Because I cannot choose all 3 to be 0. They have to sum to 1. Fortunately, there is a very good mathematical property that the interpolation in this middle cell, between here and here is actually monotone. The oscillation is happening next to the discontinuity, but not in the discontinuous cell itself. This you can prove is a mathematical theorem. So near the center of the hurricane or whatever, at the center of this, this wind, there's nothing. The eye of the rotation, there's nothing there. It's the disturbance is around it, but not at the center. At the very cell that contains the discontinuity, all interpolations are monotone, no matter how high order. This you can prove. Actually, the proof for this initial data, the proof is very simple, because if it is a polynomial of degree 2, the derivative is a polynomial of degree 1. It has only 1 0, right? It has only 1 0, but that 0 is between here and here, because the values of the function are the same, mean value theorem. So there is a point in the middle for which the derivative is 0, but there is only 1, so that leaves you no room to have a 0 here. So if the derivative has no 0, it has to be either positive or negative, meaning monotonicity. Of course, this is just a proof of the simple case, but you can make it a theorem which can be proved by undergraduates that works for general piecewise smooth functions. So this assures this very simple-minded Wayno reconstruction achieves the purpose of essentially non-oscillatory. In other words, the overshoot happens only at the delta x to the power 4 level, so it will not have this order 1 overshoot. So it's very simple-minded way of achieving this purpose. Okay, so how do you, now this is remember this is the wish list, right? How do you achieve this wish list? How do you choose data, WK? Well, there are many ways, but the most commonly used way is this 1906 paper. So basically, you have the linear coefficient. You scale them by the smoothness indicator called beta k. And the beta k is defined this way. Okay, so you want to measure how smooth your function is in that interval. So how do you measure it? Okay, a function is smooth if its derivatives are small, are not big. So this way, you measure the first derivative, you measure the second derivative, you measure their L2 norm, well, L2 norm squared, and you put those coefficients in front so that it's a scaling invariant. I don't want to explain the details. And then that gives you this beta k. So beta k measures how smooth the function is in the cell ik. And it is put to the denominator. So if the smoothness indicator is big, meaning the function is less smooth, then W delta K will be smaller, right? So that is correct, right? We want to assign less weight to a stencil which is not so smooth. So this is simple formula. It will work. It will work. And you might say, oh, this is a terrible formula. ChatGPT doesn't know how to code this. So you have to work it out yourself, and that's it. It's just formula, right? So you tell this to the ChatGPT, then it can code it for you. Okay, so that's it. So the Wayne procedure is very simple, right? You first compute those betas based on cell averages. And then once you compute those betas, you put them here. Remember, the gammas are just constants I listed, 1/10 and so on. So then you get those unscaled nonlinear weights. You scale them to sum to 1, and then this will be a nonlinear weights, and then that's it, right? Then you get the polynomial approximation. So quite very simple, very simple. So some remarks. The first remark is that this thing is not so good. This linear weights, this 1/10 and so on, they depend on where you put the approximation. If you move the approximation point a little bit, the linear weights also changes. So that's a little bit of work, especially for moving meshes, right? Moving meshes, you have to recompute this every time. And also, if you get a weight which is negative, then you get trouble, which you have to figure out how to handle the trouble. For that purpose, I would recommend that you use the more recent so-called multi-resolution Wayne, which would actually build approximation based on arbitrary linear weights, not this 1/10 and so on. So you can, in this procedure, you are allowed to take the linear weights to be anything which sum to 1. And you can still obtain this two-wish list, namely, it is high order in smooth regions, and the non-oscillatory one, there is a discontinuity. So this is a little bit more friendly if you have multidimensional unstructured meshes, if your mesh is moving with time, and so on. The other thing is that the non-smooth indicators that I indicated above, which for fifth order is in this paper, for high order is contained in this paper. Of course, you can say that, okay, why do you have to use that kind of L2 norm squared of the first derivative and second derivative as smooth indicators? Is there anything better, right? Yes, there are something which would work better in certain cases. Actually, when John, who was my PhD student at the time, when he wrote this paper, we were actually testing many recipes. So this was only one of the recipes that we finally adopted mostly based on efficiency. Because Guangshan Jiang told me that, okay, if you use exponential functions in the weights, then it runs very slowly because this computer code is a sine x or exponential x, epx. It's just one line, one symbol. But underneath, it's actually doing a series expansion in the summation. It's very slow. If you don't believe me, you can look at how much it costs to compute x squared versus exponential x. The exponential x is at least several, maybe 20 times more expensive than x squared. So if you have to do this repeatedly, it's actually not a good idea to have weights which depends on those complicated functions. So polynomials are fine. So yeah, but nevertheless, there are many papers in the literature discussing on how you improve on the weights and on, so I listed some of them here, so you can, so if you want to start with this business, I would say start with the very simple one, is 1906 paper of Jiang and myself, and that should solve your problem. Maybe not optimally, but should solve your problem. And then if you want to refine, you can go to one of those strategies to do that. Now, polynomial building blocks, of course, can be replaced by any building blocks, for example, exponential functions, trigonometric functions, and so on, depending on what kind of problems you are solving, right? So some functions are better approximated by, let's say, very wavy functions are better approximated by sine x, cosine x, rather than algebraic polynomials. And some of them boundary layers are better approximated by exponential functions rather than polynomials. Then you can do the same thing, can do based on those things. Okay, so this is a very short description on the very backbone, right? The approximation procedure. I used the reconstruction, but you can also use interpolation. So that is given data values. How do I get piecewise polynomials to approximate the data? So that you have both high order accuracy in smooth regions and non-oscillatory performance near discontinuities. Now I will try to use it in the scheme itself. So let's say I want to solve this PDE. Now I want to solve it, let's say, in the finite volume fashion, which is I integrate this PDE over cell ij and divided by the cell length, I get 2. 2 is not a scheme. It is the same PDE, but integrated over cell ij and divided by delta xi. So if you to convert this into a scheme, what you need to do would be you start with the information of u bar I at time 0. You want to compute an approximation to f of ui plus half, and then put them here. Then you can update this by longitudinal or whatever to u bar I at the next time level. So the key thing would be, given the cell average information, you want to get a good approximation to ui plus half. So this is exactly the reconstruction I mentioned. So that is why reconstruction is so popular. In fact, actually, you don't reconstruct just one value at I plus half. You reconstruct 2 values, one from the left, the other from the right. And that is why this biased stencil. So if it's biased to the left, I would get the approximation called u minus. If it's biased to the right, I would get the approximation u plus. You double the amount of work. However, this would allow you to tune the numerical viscosity. So you, through this so-called numerical flux f hat, which is based on either monotone numerical flux or approximate Riemann solvers. So this, I will not go into the details, but it is, you will remember that the purpose of doubling the amount of work here is to allow you to get suitable upwinding, suitable numerical stability for solving complicated hyperbolic problems. So this f hat, there are many studies on the choice of this f hat, the Godunov flux or Quisosha flux or Las-Fridges flux and so on. You can pick any one of them. Doesn't matter which one you pick, it will always be high order. The reason is that both u minus and u plus approximates the same function at the same location. So if it is continuous there is a very little difference between these two. So no matter what the f hat is, you get high order accuracy. And near discontinuities, these two will be very different. That will provide you with the correct upwinding. Because this f hat, we may be using more information from u minus or using more information from u plus, depending on how the wind blows. So, okay, so that's it. So these are the examples of the fluxes that you use, 3 fluxes that I wrote. And then, yeah, so you basically, as I explained, you use these 5 guys to compute u minus and use these 5 guys to compute u plus. You can see that it is up in the bias, right? I plus half is here. So that means you have 3 to the left, 2 to the right. So that means it's u minus. And the other one is 2 to the left, 3 to the right. So it's U plus. Okay. Now, how about the finite difference? It's very, very similar. So the only difference is that there's no bar here, which means I'm given the point values of the function and I evolve those point values also by this conservative scheme, this f hat. But this time, physically it's less clear, right? So what is this f hat, right? Before the f hat was very simple because I have integrated, the f hat should be f of u j plus half, but here it looks like very artificial. So what would f hat be? However, it turns out that it's not very big deal that you can really get a meaning of this f hat through this very simple lemma from calculus. It says that, okay, if you have f of ux as a function of x, if you can find a function called h of x, which actually depends on theta x, h of x, such that f of ux is the sliding average of h. So if equation 3 holds, then if you take x derivative on both sides, evaluated at xi, you find out this is a fundamental theorem of calculus, right? You have x here, you have x here. You take the derivative with respect to x. You first freeze this, take the derivative with this thing, you get h of I plus half. And then you take the derivative with this lower bound, you get a negative sign h of I minus half. So this equality is a consequence of this definition. But this equality tells you that, okay, this f hat I plus half should be exactly h of I plus half. It's the same thing, right? Plus difference. So if you have a way to approximate h of x, you are done. You can then use it as f hat. So how do you, this h of x seems to be defined indirectly through 3, right? This, remember, this is what you know, f of ux. You know the point values of this guy. But you want to find the h of x, which looks funny, right? It's the integration of this equals to that. But it's not really funny because you can see that this thing, if you evaluate the right-hand side at x equals xi, then this is just xi minus half to xi plus half of this unknown function h integrated over the cell size, divided by the cell size. But this is nothing but the definition of cell average of h. So even though I have no idea what this hx is, I do know that its cell average is this f of ui, which I do have. Because I'm a finite difference, right? Finite difference, I know ui, so I know f of ui. So I know this unknown function h of x. I don't know function itself, but I know it's a cell average. If I know the cell average, and I would like to have the value of h at I plus half, I know the cell average, I would like to know the value of h at I plus half. That's exactly the reconstruction that I described before. So it's basically ended up to be a reconstruction again. So this simple lemma allows us to kill, how do you say that? Kill 2 birds with 1 stone or something like that. So you have one subroutine which does the reconstruction from cell average to point values. You can use the same subroutine both for the finite volume, which is more natural, and for the finite difference, which is less natural, but you can see from this simple mathematics that it is true. Okay, so this is what I'm saying, right? Same subroutine with u bar I as input, and then f of ui as input for finite difference. The output here will be u plus minus I plus half. The output here will be f hat I plus half. So at the end of the day, the same Wayno procedure that I described before, the reconstruction procedure, can be used to design schemes for solving hyperbolic conservation laws, both in finite volume fashion and in finite difference fashion. Okay. So here are more details that I will skip. So you still need the stability, right? You need upwinding, so then you need to, the finite difference, you need to do a little bit of flux splitting. Now, let us compare finite volume and finite difference schemes. Finite volume schemes involves reconstruction. It can use any monotone flux. It does not need uniform or smooth meshes. It actually also works in 2D in triangular mesh. But unfortunately, of course, I described it only in 1D. In multi-space dimensions, the reconstruction is actually quite costly. So there's a large computational cost for 2D and especially for 3D problems. So this color is the good thing. This color is the bad thing. Finite difference is just the other way around. So it can only use limited amount of monotone fluxes, for example, large fridges. It needs uniform or smooth meshes. These are the cons. These are not, comparing with finite volume, these are the not so good properties. However, it has one good property which overrides all these bad properties, namely it has smaller computational cost for multidimensional problems. Really smaller, really smaller. So those of you who wrote codes for 3 dimensions in both finite volume and finite difference fashion, you will find out that latter, the finite difference runs much, 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 much faster. So that kills, that one single property would make these disadvantages less important, right? So you really want something to run fast. Okay. There's some remarks that what I described is good for scalar cases. Now for systems, it's actually not mathematically, you can say systems are very tough because up to now, you really know very little about the solutions in hyperbolic systems. So existence, uniqueness, well-posedness, very, very little. But I still want to compute them. So this poses difficulties, but it turns out that in practice, the same algorithm that we designed for scalar cases works very well for systems if we perform the so-called local characteristic decomposition, which I don't want to explain what it is, but it's enough to say that it costs you a little bit. So you would have to, at each location, try to find another set of variables, are the so-called characteristic variables, which are computed from your original conserved variables by a matrix product, matrix vector product. And then you perform your Wayno in the so-called characteristic variables. And after your computation, you turn back to the original physical space. So going forward, going backward, both as matrix vector products. So these are additional costs. Unfortunately, they do cost you, and which there are some ways to sort of elevate this cost a little bit, reduce this cost a little bit, but not completely removing them. So this is the drawback. But fortunately, it actually works. So with very little theoretical backup, it has backup for linear systems that you can prove that this works. But for nonlinear system, it's just it's just experience, just experiments. Because nonlinear systems, you can prove very little. The reason is that we know very little about the solutions to the hyperbolic system, nonlinear hyperbolic system. Existence, uniqueness, well-posedness, we basically know. I shouldn't say nothing, but very, very little. So if you don't even know the PDE, I cannot demand that the numerical schemes to have certain properties. But anyway, the good news is that it works very well in practice, at least for equations from the CFD. It works very well. So this, I don't think I will go through. So this is the so-called alternative Wayno. I will skip this. I will skip this, yeah. So recent developments, I don't think I want to go too much about the recent developments. The reason is that there are many, you can see that the citations are a few thousand citations. So these type of papers are usually 2 categories. One is they are trying to improve algorithms themselves, trying to improve the weights, trying to improve the way it is implemented, and trying to prove smoothing indicators and so on. So these are one type of papers. The other type is application. So it's really applied to many, many different things. So the reason is that this scheme, even though it looks simple, it's actually very hard to beat. So basically, if you code it right, you find out the correct hyperbolic structure, you code it right, it will work. It's almost 95% sure. It will produce you something, and that something is usually very good. That 5% which doesn't work usually corresponds to trouble beyond the design of Wayno. For example, if you get a negative density, you get a negative pressure, and then your PDE becomes bad. It's a hyperbolic PDE becomes an elliptic PDE, and then certainly any scheme will fail. So if that happens, you need to figure out how to avoid the negative density, negative pressure. And here, for example, the well-balanced. So these are sort of things beyond the original design of Wayno schemes. So they are saying, okay, I have shallow water, I have a certain equilibrium, I have small perturbations over the equilibrium. So can my scheme keep the equilibrium exact, still water or whatever equilibrium exact? If I can keep this exact, then I have a so-called well-balanced scheme. But keeping them exact is very difficult. The reason is that these so-called equilibrium solutions are not polynomials. They are just funny-looking functions. How can you have a scheme which has zero truncation error on such non-polynomial unknown solution? You don't know the solution, exact form of the solution either. So how do you design a scheme which has zero truncation error on that level? So that is part of the designing principle, not just for Wayno, right? For any scheme which will be very well balanced. So there are many works on doing this study. But I would say this: if you are interested, you go into the literature to read them, and the purpose of Wayno in such a study would just be the base, like the foundation break. So this is the background, right? So the backbone of the scheme is this reconstruction procedure. That's the workhorse. You use that, you are guaranteed to have a good approximation, non-oscillatory, and then on top of that, you work out all the other properties, so one by one. So that's why I would not, so this is what I'm saying, that if you go out of the bound, you are in trouble. So you want to design schemes which are bound preserving and so on. But at any rate, the reason that you can do this kind of things is that the foundation is solid. You have a very good approximation procedure at the foundation. That's the Wayno reconstruction or interpolation procedure, and you build upon that. You can also use Wayno as limiters for discontinuous Galerkin methods. Discontinuous Galerkin method, I talked about it maybe last year in this Congress. It's another class of very, very popular numerical methods for solving hyperbolic equations. And they are very good for unstructured meshes and general geometry. But I think I mentioned it honestly last time also. It does have one drawback in comparison with Wayno schemes, namely its ability to control oscillations is limited. If you don't do anything, well, let me put it this way. There are recent studies on trying to, within the finite element framework, to achieve that purpose, but it's a very, very new study. Up to very recently, it's really you need to borrow ideas from Wayno or from other successful finite difference, finite volume schemes as limiters to control oscillations for discontinuous Galerkin methods. So this is again a series of work. And these are boundary conditions I won't go through. And degenerate parabolic equations I won't go through. So I described the hyperbolic equations, but of course, in the real world, you have CFD, you have Navier-Stokes. So you do have physical diffusion, which could be degenerate. For example, Navier-Stokes equations for compressible flows, you don't have diffusion for the mass equation. The mass is not diffused. Momentum is diffused. the total energy is diffused. So then it's a so-called degenerate parabolic equation. Then the difficulty would still be how do you handle the hyperbolic term. So this you can then work in this direction. And some examples, and then we will quit. So example 1 is a shock vortex interaction. So basically the flow is a shock. I think, how does it work? Maybe it's shock is here, the vortex is here, shock moves, hit the vortex, and then you get this complicated structure. Shock hit the vortex. Then once it hit the vortex gets broken and gets all kinds of pressure waves. These are the acoustics. So this lousy airplane sound is coming from this, basically the shock interaction with the vortex structure coming from the tip of the wing. And then you get this noise which propagates very, very long. So to simulate these kind of things, you need a scheme which is essentially non-oscillatory to resolve the shock very well, and then very high order to resolve the vortex and its interaction with shock very well. So if you think about if you have a Gibbs, your numerical solution already have a 10% overshoot comparing with the shock strength. But this vortex strength is maybe only 2% of the shock strength. So your numerical artifact is way bigger than the vortex itself. Then you have no hope to resolve this interaction. So you really need something which has very faithfully obeyed the shock with no oscillations or very little oscillations, and then high resolution for the vortex. So that for this we know is perfect. So this you can compute and get all these nice results. The other thing is Mach 2000 flow from astrophysical jets. This Mach number is very, very high. You get this solution now. It looks naive enough, but it's very difficult to simulate because of this very, very high Mach number. What it means is that it will be, the energy will be almost completely kinetic energy. So the internal energy is only a very small percentage of the total energy. So that way, if you take the total energy, subtract the kinetic energy to get the internal energy and the pressure, chances are you get a negative internal energy or negative pressure, then the code blows up. So then for this particular case, you really need the study on the positivity preserving technique. Okay, and the third one is about boundary condition, which I will skip. I think I will skip this, yeah. Porous media. Yeah, I think I will skip all these test cases just to show that it works for the convection diffusion equation as well. I think in summary, basically, we have a very good base algorithm, which is at the heart of it is a reconstruction or interpolation algorithm, which obeys, it's a simple recipe and achieves two objectives. One is that it's high order in smooth regions, and the other is non-oscillatory near discontinuities. And then using this as building block, we can build very powerful finite volume schemes for solving both hyperbolic conservation law systems and convection diffusion equations. Okay, thank you.
Okay, so right now I think you do not consider the boundary condition, right?
Yeah, I mentioned, but I did not really go into it. So there are studies on boundary conditions.
So if we consider the evolution in spherical coordinate or cylindrical coordinate,
right,
then sometimes the evolution can be unstable at the center of axis.
That's right.
So
right.
I'm wondering whether we can apply this technique to this.
Yes, you have to be careful. Yeah, over there you really have to be careful at r equals 0. Yeah, you can do that. Yeah, but you have to be very careful. So you have to use the L'Hopital's rule at that location, because that singularity is fake. see, physically there's no singularity.
That's
there.
correct.
Yeah, yeah. So you have a way to overcome that, but there are some details.
Okay, yeah, thank you.
Yeah.
Did you say something about the entropy condition for the scalar case?
Yes,
So do these schemes fulfill the entropy condition for?
you can make them fulfill. Right.
So is there any other question? Okay, so if there are no other questions, let's thank our speaker again.